What is logic gate? Logic gate is the brain of a computer. What does it mean? Okay, nowadays, everybody is working on a computer. A computer needs to do work. It needs to do tasks set by the human, right? How does a computer do work? How does a computer carry out calculations? Okay, everything, programming, store information. How does it work? It's because of the brain of the computer. A computer has a brain, right? But it's not like the brain of a living being. So the brain of the computer, what is it made up of? The brain of the computer is made up of circuits, okay? Electronic circuits. You learn about transistor, you learn about diodes, what else? Semicon, everything. All those make up a circuit, and that is the building blocks or the core brain of the computer. Who gives the computer the brain? Answer is the human. We are the one who gives the computer the brain. How do we give the computer the brain? We design circuits. Okay, we design circuits. We design what we call as logic gates. So inside the brain of a computer, it is all circuits, and these circuits, we call it logic gate. Okay, so logic gate is the building blocks of a computer's brain. It is what helps the computer to do the tasks, such as calculation tasks, store information tasks, any tasks. Okay, now the thing is, if you want to communicate with the computer, how do you communicate with the computer? Do you use language like English? No, cannot, right? The computer cannot understand your English. Okay, so the way you communicate with your computer is you have to use their language. What is their language? What is the computer's language? You see, if I ask the light bulb, let's say I have a light bulb. I tell the light bulb, please turn on the light. Will the bulb turn on? No, that sounds crazy. Okay, so the bulb cannot understand my instruction. It cannot understand my language. It cannot understand my instruction, okay, the informations. Okay, so it will not turn on the light. What the bulb understand? What is the language that the bulb understand? The language that the bulb understand is only in the form of current, voltage. If you want the bulb to turn on, okay, if you want the bulb to light up, you have to give it an information in such a way that you allow current to pass through, right? So that is a form of information. The flow of current is a form of information. I let the current flow, the light turns on. I close the current, I do not allow the current to flow, then the bulb turns off. So I'm communicating with the bulb using information, okay, in terms of flow of current. So flow of current is also a type of information. I let current flow, and then I do not allow current to flow. Whether there's current flow or whether there's no current flow, it is how I communicate with the bulb. Understand this. The same concept if I'm trying to communicate with the computer. How do I communicate with the computer? I cannot use language. I have to use voltage, current, the flow of current to communicate with the computer. You see, in the brain of the computer, there are a lot of circuits. If I want the computer to carry out certain tasks, then I let the current in and then flow in the circuit, then it will produce the result I want. The outcome that I want based on the design of the circuit, or in other words, based on the program. Okay, I give a certain input, and then based on the programming, it gives me output. Okay, so logic gate is the building blocks of a computer. Now, what is inside the logic gates? Let me write this down. It is the building blocks. Okay, the core structure of a computer. That is the brain of the computer. We call it gate. Okay, logic. Now, what is inside the logic gate? It is just a bunch of circuits. Very complicated circuits. We are not going to look at it. Just a bunch of circuits, okay, that makes up logic gate. So this is the brain. What we do, what we put input, we give it input. Then according to how the brain is programmed, it gives us output. What is that input? That input is in the form of current. Okay, the input is in the form of current. That is the language of the computer. So we let current, if current is present, general, we would use a 1. And if current is not present, there's no current, we give it a 0. That is why you always see this 1 0 1 0 1 0 in the matrix, right? If you have watched the movie, matrix movie, 1 0 1 0 1 0. Okay, so that is flow of current. 1 is there's flow of current. 0 is there's no current flowing. Okay, so 1 0 1 0 1 0. This is how the computer store information using 1 0. Because you see, 1 0 1, if I have 3 digits, right? How many possibilities? I can go like 1 1 0 0 1 1 0 1 0. Many possibilities. If I add in one more digit, then even more outcomes I can get. So this is how it stores information. Okay, so just to give you a general idea, what is a logic gate? Okay, yeah. Now in the next part, you are going to see, of course, we are going to deal with this 1 0 thing. Okay, now to understand logic gate, the more detail, wait, okay, wait, something's wrong. Wait, okay, let me clear this. Okay, let me go to the next page. Now, to understand logic gate, I'm going to tell you a short story. Let's go to the next page. I think something's wrong with my screen. Let me reshare the screen. Sorry. Let me reopen the file. OK， 老师的那个file hang 了一下啊 ，force quit 它先。I force quit my OK。Okay, now you should be able to see my slide back. Just now my slide already hang. Now it should be fine. So you should be seeing my slide. Okay, again, sorry for the delay. Okay, let's continue, guys. Let's continue. Right, so you get an idea now. What is the logic gate? So let's see how it works and what really is a logic gate. So I'm going to tell you a short story here. Let's say there is a manager who owns a bank. We call it Bank of MHT. Okay. Now, one day, there is a robber came in to rob the bank. Okay. Now, nobody recognized this robber because maybe he had his mask on. Okay. Nobody sees his face. But it is reported that the robber is short and fat. Okay. Short and fat. Okay. Short and fat. But we don't know how he looks. Now, this bank of manager, he is worried. So he's worried that the robber might come back and rob his bank again. So he's going to hire a manager. Sorry, he's going to hire a security. So he hires a security guard that helps him guard the bank, guard the door. Now, this manager, right, he tells his security guard, he gives a certain instruction. He tells his security guard that you only open the door to person who is thin and tall. Okay, so you can see here, thin and tall, open door. Person who are fat and short, you don't open door for them because the robber is short and fat, right? So you only open the door for thin and tall. Okay, now what the manager is doing here is that he is giving certain instructions, okay, to the security guard. Then the security guard is going to analyze. Based on this instruction, he will make his analytical judgment to whether open the door or not. Okay, so say that one person comes in and the person is tall and short. Okay, so he has to make this judgment. Okay, based on the instruction, do I open the door for this guy? Okay, and then after he makes his judgment, he has to whether open or allow or do not allow. That is an outcome. Okay, so the process of the security making this judgment is a logic process. Okay, because it is a very clear instructions. If it's thin, you open door. If it's tall, you open door. Very clear, very logic. Okay, it's either thin or short, tall or short, thin or fat, right? It's a very logic process. So this process of judgment is a logic process. Now, let's say the first person comes. Okay, now we are going to set a reference that if the person is thin, then we will put a 1. Okay, just like the 1010. We are going to take it as a binary. Binary means it's either this or that. There's no something in between. Either this or that, either thin or short. So if it's thin, I will put it 1. If it's if it's fat, then I'll put it 0. Now, same thing. If it's tall, let's say tall, I put it 0. Okay, and if it's short, I put it 1. Okay, so the first one. Now remember our instruction. What is our instruction? Thin and tall. We want to open door, right? So the first customer comes, and this customer is thin and 1. Okay, 1 means that he is thin and he is short. Okay, now sorry, I think this one should be 1. Tall is 1 and this one is 0. We do a bit of correction, easier. Okay, thin and tall, we do 1 and 1. Fat, short, we do 0, 0. Okay, so the first customer comes 1, meaning that he is thin and he is tall. Do I open the door? The security, does he open the door? Yes, because the instruction given is thin and tall, open the door. So yes, open the door, 1. Now, the second customer comes, thin and he is short. Does he open the door? 1 thin, Cannot, right? Cannot fulfill. It does not fulfill the instructions because it must be thin and tall at the same time, right? So this one, the security does not open the door. Close it. Okay, do not allow. The third customer comes. Third customer is fat. Okay, 0 means fat. And then he is tall. Okay, he is tall, he fulfills, but he is fat, not thin. So he is also not allowed to pass, right? So this is also closed door, do not allow. Now the last customer comes, okay, neither is short and, okay, short and fat, 0, 0. Does the security open the door? No, 0 also, right? So this is the outcome, okay? This is based on the input, which is the customer, the input, whether it is thin or tall or short or fat, then the security has to make a decisions. I open the door or I do not open the door. So based on this manager's instruction, the security only open the door when the customer is thin and tall. Now, what happened here is the manager found out, okay, if I only allow customers who are thin and tall to come in, then I will lose a lot of customers, right? Because all these potential customers, you do not allow them. So I will lose a lot of customers. So what happened is that this manager, he wants to change his instruction. Okay, he changed his instruction to this. So he gives the security a new instructions. He says to the security, he says, okay, you only open door to customers who are thin or tall. Okay, now there's a difference here. This one is you only open to customers who are thin or tall, meaning that either one is fulfilled, then it is allowed to enter. Okay, either one is fulfilled, it is allowed to enter. Okay, then again, the next day, the security has to make his judgment. Okay, the first customer comes. All right, first customer comes, thin and tall. Does he open the door? Yes, right, open the door. Second customer is thin but not tall. Does he open the door? Answer is yes, right? Because one is fulfilled. Okay, one is fulfilled. So this is also 1. Come again, the next one, 0, 1. So it's not thin but tall. 1 is fulfilled, yes, allowed to enter. So he can enter. And last one, okay, neither one, 0, 0. So this is the only type of person not allowed to enter, 0. Okay, so by doing this, then he has more customer comes in. Okay, now he realized another problem again. What happened is now there are too many customers come and go. All these customers, they don't like the security guard standing there for whatever reason. Okay, they don't like the security spying them. Okay, so they make a complaint, and now the manager says, okay, I want to replace the security. I want to replace this guy, this security. I want to replace it with a computer, with a logic gate system. Okay, so how does he replace this with a logic gate system? Now, in a logic gate system, they use sensors, because with the security there, right? If the security is there, then the security is the one that is observing whether it is thin or tall or fat or short. So it is he's observing, this information is coming in and he has to make a decision. How does a logic gate get the information? Because the logic gate cannot see, it cannot observe, it cannot see who is tall, who is short, right? Unlike the security guard. It's not a person. So the logic gate only sees the current. So the information that the logic gate understand is in the form of current. So we have to use sensors. Okay, we have to use sensors. Okay, now the manager put 2 sensors here. Now the security is gone already. He got sacked. Okay, now we got 2 sensors. First, he put a sensor at the door here. At the door here. Now he set the height about 5 feet. Okay, just pick a random number, 5 feet. You put a sensor here. So what happened is when the customer come in, if the customer is higher than this 5 feet, then the sensor is going to send a current to the system, meaning that they will detect it is tall or short by sending the current. So the manager thinks that, okay, if it's higher than 5 feet, then I will consider it tall guy. If it's lower than 5 feet, then it is a short. Okay, so he put a sensor here. So whenever the customer pass through, if the customer is higher than 5 feet, then the sensor, beep, it will send a current to the system. Okay, so you either get 1 or 0. You either get tall or short. That is the information that comes into the logic gate. Okay, now how about the what, thin, whether thin or fat? Okay, so the manager put maybe he put a carpet here. Okay, he put a carpet here, and underneath the carpet is like a weighing scale. It's like a hidden weighing scale. So when you stand on a carpet, it shows your weight. Okay, but without them knowing. So this is a weighing scale. Now he says that, okay, if it's higher than 60 kg, then I will consider them fat. If it's lower than 60 kg, then I will say they are thin. So again, the system will detect there's a sensor here. Okay, so if it goes higher than 60 kg, then the sensor is going to send a signal 1. If it's lower, then it's not going to send a signal 0. So the current flow or the current not flow, produce or not produce, it depends on a certain criteria that has to be fulfilled. Okay, so if it's like this one, bigger than 60, it fulfills the criteria, then it will send a current. These are the 2 information that the logic gate can understand. So he sends in this 2 information to the logic gate. And what happened to the logic gate? The logic gate has to make a decisions, just like the security guard. Whether I open door or I do not open door for the customer. Okay, so this is the basic idea behind the working of a logic gate. What is inside this logic gate? Basically, it's just circuits, transistor, diodes, everything together. Okay, what you are giving it, what you are giving the system, you are giving it current in the form of 1, 0, whether there's current or no current. You are giving it current and it makes a judgment. So I can draw my diagram like this. This is the logic gate. Logic gate. And then here is my input in the form of current, and it is going to give me an output in the form of an action, whether it opens or do not open. Throughout this process, this entire process is very logic process. Either this or that. There's no something not sure. No. You cannot say I'm not sure. No, it's either this or that. That's why we say logic. Okay, gate means whether I allow or I do not allow. Okay, so that's logic gate. Now, how many types of logic gate are there? Now we are going to we're going to look at how many types of logic gate. Okay, we are done with this. So let me go to the next one. Okay. Let's look at the types of logic gate. The first gate is AND gate. AND gate, you have to make all capital. Okay, AND gate. What is the AND gate? AND gate looks like this. You have to remember the diagram. Okay, so it's like a D, like this. Looks like a D, and then we have two input. I'll call this input A, input B. It gives us a output. This is the diagram of the AND gate. Okay, now we can have two input, we can have three input, or many more. But in the SPM, we only study two inputs. Okay, no need to study three inputs, only two inputs here. Okay, now the AND gate, and what is important also is the Boolean expression. Okay, Boolean expression. What is this thing? Boolean expression, it represents this gate. It's a formula, a expression that represents this gate. So the Boolean expression of this AND gate is A dot B equals to X. Okay, so the dot means AND. Remember this AND gate? This is like the security guard. The first one, the first instruction given by the manager, right? You open this, if it's thin and tall, that is the AND gate. Okay, so must be two fulfilled, then only you get the outcome. The Boolean expression is very important. You need to remember that one, this one. And what else to remember? Of course, the diagram of it. Okay, and also the most important thing is the truth table. Okay, guys, the truth table shows all the possible outcomes. Okay, first one, input, we got 2, AB. And then output, we got X. Okay, now we have 0, 0. We will write all the possibilities of the input. 0, 0, 0, 1, 1, 0, and 1, 1. Okay, these are all the possibilities. 0 means no current, remember, and 1 means there's current flowing in it. Okay, so meaning that this one, the input, 2 input has no current. What is the output? The output also no current. This one input got current, 1 does not have current. What is the output? The output is also no current because this is an AND gate. It has to be fulfilled 2. If only 1, cannot. Okay, so 1, 0 is also 0. And 1, 1, then I get current. This only I allow it. So when you put 2 current, if you use AND gate, if you use AND gate, 如果你用这个 AND gate, 你这边有 current flow, 你这边又有 current flow, 它这边才会有 current flow. 一个没有 current flow, 它这边就不会开，它就会也是 remain 没有 current flow. So 两个一定要 fulfill. 那个是 AND gate. Okay? Now, how does the circuit looks? The circuit looks like this. Okay, if I draw it, let me get some space here. The circuit of the AND gate is like this. Resistor. Let's say here I have a bulb. This is the battery. 2 switch A and switch B. Think of the input as the switch. So AND gate means 2 have to be closed, then only the current flow, right? 1, 1, and only 1. So meaning that this one, you have to close this, you have to close this, only the current will allow to pass. If you close 1, but 1 is not closed, no current flow. So this entire circuit is the AND gate. Okay, remember I said the logic gate inside is a circuit, right? So this is like the circuit. Okay, this is the circuit, just to give you the idea of this. Okay, like next one, let's go to the next one. The next one is OR gate. Okay, now OR gate looks like a rocket. This is curved and like this. Here we have our two input, A, B. Then we have this output X. Okay, now the only thing you differentiate, how you differentiate the AND gate and the OR gate 呢？你讲 differentiate 这两个，这个如果它是直的，它的后面是直的，它就是 AND gate。这个如果它后面是弯的，它就是 OR gate。OK， 因为有时候它会画到这样啊，它画弯，然后它画很像一个 D 这样啊，所以你会 confuse， 哎呀，这个是 AND gate 还是什么？所以你要讲看，你看它的这个，它是弯还是它是直的 ？OK， 所以总之是弯呢，它就是 OR gate。Boolean expression for OR gate is A plus B equals to X. Okay, this is my Boolean expression. Okay, again, come to the truth table. AB, and then we have our output X. For the OR gate, the OR gate is the same as the instruction given by the manager, the second one. Remember, the manager says, if it's thin or tall, he can pass. It's the same thing as this one. So if it's thin or tall, so either if it's 0, 0, then you get 0. 0, 1. 1 has current, then it is allowed. 1, 0, 1 has current, it is allowed. And also 1, 1, then it's 1. This is the outcome for the OR gate. How does the circuit looks? Resistor. Then we have a switch here. Okay, the bulb is here. Circuit look like this. This is an example of a OR gate circuit. You see, point A, point B. If I open switch A, if I disconnect switch A, and I close switch B, is there current flow? Yes, because current can flow in the outer circuit, even though switch A is disconnected. So there is current flowing, this one. Okay, switch A is off, switch B is on, then it's on. Same as this one. If switch A is on, but switch B is not on, still there is current flow in the circuit, this one. So it's 1. Okay, so this is an example of an OR gate. So when both are switches on, then you get 1. Let's go to the next one. The next one is NOT gate. What is a NOT gate? Okay, a NOT gate is different from these two. A NOT gate only has one input. The symbol is like this. Okay, how do you differentiate a NOT gate and the rest? When you see this circle, you see the circle at the front. Okay, 这个小圆圈呢，这个就是 NOT gate. 你看到有这个圆圈就是 NOT gate. Okay, this is a NOT gate. Right. So the input is only one, A, and the output is only one. NOT gate is very easy. Okay, the truth table, because it only has one input, right? So A and X. If the input has current, then it will reverse it. Output is 0 because it's a NOT gate. So not A, it will reverse it. If the input is no current, not this, so it's 1. It inverted. Okay, so that is NOT gate. The Boolean expression is A, and then we put a bar here. This one is pronounced as bar. A bar. Okay, A bar equals to X. It means not A. Okay, Whatever is A, the outcome X is not A. That is the NOT gate. Example circuit of a NOT gate. The switch at the middle, then we have the bulb here. You see, if the switch is disconnected, is there current flowing? Yes, right? The current can flow in the outer circuit. Here, 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 here. If it's disconnected. So it's like this. When A is 0, okay, switch A is disconnected, then there's current flow. X is 1. When I close the switch, what happened? Is there current flowing through the bulb? Answer is no current will flow through the bulb. Why? Because when you close the switch, this creates a short circuit, right? This wire has no resistors in it. So what happened to the current? The current will only flow in the bridge here. It will enter here, and then it will go back to the battery. It will not flow past the bulb because you have created a short circuit. Remember, current always choose the least resistance path. So if you close this switch, then it will go here. So does the bulb light up? No, no light up. Okay, so 1 is 0. This is example circuit of a NOT gate. Okay, these 3 are the basic one. There are 2 more, then we are done. Okay, there are total of 5 that you need to remember. Okay, you can take a screenshot of this if you want. Now we go to the next one. Okay, what you need to know, what is important here? First is the truth table. You need to know how to get the truth table, and also you need to know the Boolean expression. Okay, let's go to the next one. Okay, next one is the NAND gate. What is a NAND gate? Okay, a NAND gate is like a NOT AND gate. Okay, let me draw it. The NAND gate looks like this. It looks like an AND gate. AND gate is like a D, right? With a circle in front. Okay, if it has a circle, then that is NOT. Plus this one is the AND. So it is NOT AND gate. 2 input, AB, output, X. Okay, so this is, let me draw it here. This is the AND gate, and this is the NOT gate combined together, meaning that I can draw this as well. It's like an AND gate, and then I join to another one in front. This is the NOT gate, and then we get the X. Okay, we have an AND gate and we have a NOT gate. This is the same as this one. Okay, just to let you see, I can put my diagram like this. It's the same thing. Meaning that I go AND gate first, I pass through the AND gate first, then only I pass through the NOT gate. Okay, Boolean algebra. Boolean expression is A. What is the expression for AND gate? AND gate is dot, right? A dot B equals to X. But I have another NOT gate here. So AND gate, if I want to add the NOT gate, then I put a bar for both. Okay, meaning that whatever is the A and B, then I NOT the entire thing. A dot B bar. Okay, that is the Boolean expression for the NAND gate. Truth table. Okay, we have 2 input, AB. and then we have an output X, right? Okay, let's see. 0, 0, 0, 1, 1, 0, and 1, 1. First, we solve for the AND gate. We got two, so we solve for the AND gate first. So if it's 0, 0, let me put one column here. That is the AND gate. 0, 0, 0, 0, 1, 0, 1, 0, 0. Only two fulfilled, then it's 1. This is for the AND gate, right? And then we have a NOT in front, right? So you have to NOT AND gate. So the X is NOT whatever is the AND gate here, I take the reverse. So 1, 1, 1, 0. That is my outcome. Okay, that is my outcome. If I have a current here, input A, and I don't have a current here, input B, what happened to the outcome? You see the third one. Okay, you got current, you don't have current, the outcome is current. So here you will have a current. It will allow the current to pass. If this is the NAND gate. Okay. Circuit, this one we don't need to know. Okay, we just need to know the basic one. The last one. Okay, last one. The NOR gate. If NAND is not AND, then NOR is not OR. Okay, so how does it look? We have an OR gate, and then we have a circle in front. Two input, A, B, and then we have the output X. So this can be written as, me draw another circuit. This can be written as 1 OR AB, and then it goes to another NOT X. Okay. All right. The Boolean algebra, again, we write OR gate. OR is a plus, right? N is a dot, O is a plus. So A plus B equals to X. If it's not OR gate, then not the entire thing. A plus B bar. What is the input? A, B, X. Okay. 0, 0, 0, 1, 1, 0, and 1, 1. First, we worked out the OR gate. 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. The outcome is whatever is the OR gate, I not OR. Okay, so 1, 0, 0, 0. Let's wait for 5 seconds because I see internet is unstable. If it's lagging, you have to let me know, guys. Don't keep quiet. Let me know if it's lagging. If like you find it very difficult to follow. Okay, 5 gates. 5 gates, you need to know truth table, Boolean expression, and the symbol. Now, let's look at examples. What are the type of questions that might be asked here? Now, before we go to the examples, I'm going to give you a break of 3 minutes as usual. If you want to go to toilet, you go to toilet. You want to drink water, you drink water, and then you come back after 3 minutes. Okay, we'll continue after 3 minutes. So 7:55. Okay, we are back. Let's continue. Examples. Example 1. Okay, you should be seeing my screen. You should see example 1. Here I have a combination of circuits, right? So not only one, I have 3 here. What is this? This is AND gate, and this is NOT gate, and this is OR gate. Okay, I want to find the outcome X if I give it an input of AB. Now, the way we do it is like this. First, you see, you take all the A, 0, 0, 1, 1, we put it here, 0, 0, 1, 1. B, 0, 1, 0, 1, we put it here, 0, 1, 0, 1. First, let's find out what is C. Okay, now you can see B is connected to this one, right? So I can write 0, 1, 0, 1 at the leg of the AND gate. Okay, so we have 0, 0, 1, 1 and 0, 1, 0, 1. Now, then you do the AND gate. AND gate, remember, only 2, 1, it is a 1. So 0 match with the first 0, 0. The second 0 match with the second one. 8, 0, and 1, that is also 0. The next one, 1 with the 0, 0, and 1, 1, 1. Okay. Oh, sorry. I think I mislooked this one. This is a not AND gate, right? This is a NAND gate. Because there's a circle in front. And this is a not OR gate. This is a NOR gate. Okay, I made a mistake here. Okay, this is supposed to be AND gate, NAND gate, guys. Okay, NAND gate, because we have an AND gate and a dot here. So this is a NAND gate, right? So first, doesn't matter. We do the AND gate first, and then we inverse the AND gate. This 0, 0, 0, 1 is the AND gate, right? So if it's not AND, then I would take 1, 1, 1, 0. Okay, this is what I cross out. So at C, the outcome of C is 1, 1, 1, 0. I write it down here, 1, 1, 1, 0. Okay, let's see D. This is the NOT gate. Okay, so whatever is the input, we take the inverse of it. So B is input 0, 1, 0, 1, so it becomes 1, 0, 1, 0. Okay, 1, 0, 1, 0. So D is 1, 0, 1, 0. Now then you continue to X. 1, 1, 1, 0, I put it here, 1, 1, 1, 0, and this is 1, 0, 1, 0. Okay, this logic gate is the OR gate, right? OR gate. So 1, 1, 1. 1, 0, 1. 1, 1, 1. And 0, 0 is 0. So you get 1, 1, 1, 0. I write it down here, 1, 1, 1, 0. That's it. Okay, 1, 1, 1, 0 here. So whenever you want to solve this, right, whenever you want to find the outcome, first you copy down in the diagram. Okay, don't use the table to solve it because sometimes it's very hard to see. Okay, you just copy the whole thing, you put it in diagram, copy the whole thing, put it in diagram, and then you solve it in the diagram. The final outcome, then you copy down in the truth table. Okay, now how about the Boolean expression? If I want to write the Boolean expression, what is it going to be? Because here I have 3 logic gates combined together. For the Boolean expression, first, I write down a few expression out. Let's write the one at C first. Okay, we look here, the C. Now, we know that C has the input of AB. And what gate is this? This is a NAND gate, right? A NAND gate. So C, I can write the Boolean expression C is equals to A and B not. That is the NAND gate here. Okay. Now, how about this one? Add here. I will pause for 5 seconds because I see lagging. Okay, let's continue. Now, if I want to write the Boolean expression at this part, then this is a NOT gate. So D is equals, okay, the outcome is equals to B, and then we buy it, okay, not B. So we get these two expressions, and there's one more, right? There's one more at the end. This one is we write X equals to, this is C coming in and D is coming in. And this is a OR gate. So I will write C or D. C plus D. Okay, because OR is a plus. Okay, we go slower. So now I will put this one in here and I'll put this one in here because I want the expression to be X and the input. Okay, the input is AB. So my equation must be AB. So I put the C in here. I get, continue down here. X equals to, I just copy inside A dot B bar, and then plus B bar. Like this. Okay, so this is my Boolean expression. If they want you to write it out. The Boolean expression for the complete circuit. Okay, so that's example 1. Okay, I'll show you a few more, okay? A few more. Let's look at example 2. For example 2, okay, identify the logic gates. Here we have a NOT gate, we have a NOT gate, we have an OR gate. Okay, so we copy down the numbers in. A is 0011, so 0011. B is 0101. Let's find C. Okay, C is NOT gate, so I just inverse it, 1100. This one, NOT gate, inverse it, 1010. Okay, then this one goes to X. So 110 here, and this is 1010. Okay, you follow the line, it goes here, so it's the same thing as here. Now, then we do the OR gate for the X. Okay, 111, 101. The third digit, 011, and 000. 1110 is my outcome. Okay, so C, I just copy down 1100, 1010, and 1110. Okay, finish my truth table. How about the Boolean expression? Okay, write the Boolean expression. We start with this NOT gate. C equals to not A, so A bar. This one is D outcome equals to B bar. And for this one, X equals to, what is the input? The input is C and the input is D. So OR gate is C plus D. Okay, so then we substitute inside. C is A bar plus D is B bar. So that is X. Okay, A bar plus B bar. I can also write this as A plus B bar. This is my Boolean expression. Okay. Right. Example 3. You go to the next one, huh? Okay, again, this one we have 1, 2, 3, 4. 4 logic gates. Okay, so we do copy down, same thing, we copy down inside 0, 0, 1, 1, 0, 1, 0, 1. Okay, so you can see the leg goes here and goes to C. Let's work out the C first. C first. So this is 0, 0, 1, 1 coming in. This is 0, 1, 0, 1. What is this gate? This is OR gate, right? So OR gate 0, 0, I get 0. 0, 1, 0. 1, 0, 0, and 1, 1, 1. Okay, so must be, oh, okay, should be OR gate, right? So 0, 1, 1, 1. At least one is 1, then it is a 1. Okay, so 0, 1, 1, 1. Okay, then the same leg goes to here. So I copy down 0, 0, 1, 1, and this one goes here. 0, 1, 1, 1. Okay, this is AND gate. So must be 2 fulfilled. So 0, 0, 0, okay, 1, and 1. Okay, 0, 0, 1, 1. Then we do E. This one goes to E, so 0, 1, 1, 1. And this one from the B, it goes here, straight to here. So this is 0, 1, 0, 1. E is the same as D, is an AND gate. So 2 must be fulfilled. 0, 1, 0, 1. Okay, now from here, goes to the last one. So this is 0, 0, 1, 1. We copy down for the input first, and then we work out the output. Okay, this is again AND gate. It's the same thing. So fulfill 2, 0, 0, 0, 1. After you worked out this one on the diagram, then you copy down. Okay, 0, 1, 1, 1, and D is 0, 0, 1, 1. E is 0, 1, 0, 1, and the last one 0, 0, 0, 1. Okay, last one more. Okay, this one again we have 4. What is this? This is AND gate. This is OR gate. This is a NOT gate. This is a OR gate. Okay, 0, 0, 1, 1. 0, 1, 0, 1. Do the C first, the AND gate. So we have 2 input. The input are the A and the B. Okay, so we get AND gate 0, 0, 0, 1. Then we do the D. Here, input is 0, 0, 1, 1 from A. Okay, we trace back this path. This path. One can go both. One can go both. One input can go both gates. So B also goes here. 0, 1, 0, 1. So the OR gate would be 0, 1, 1, 1. And then you pass through this one, not inverted. So 1, 0, 0, 0. Okay, coming out from E is 1, 0, 0, 0. And 1, 0, 0 goes to the input of OR gate 1, 0, 0, 0. And this one, bring it here. Okay, so OR gate, what is this? OR gate 1, 0, 0, 1. That is your outcome. Okay, copy down 0, 0, 0, 1, and then 0, 1, 1, 1, 1, 0, 0, 0, and then the last one 1, 0, 0, 1. So based on this two input, what is the outcome you get? Focus on this two and then this one. Okay, this two and this outcome. Okay, Ken? Okay, so this is an example of solving the logic gate. So a combination of logic gates. So we want to fill in the truth table. Often you will be asked to fill in the truth table. Okay, next we will look at what is the application of the logic gate. So one of the applications, there are many applications, especially in the control systems. For example, automatic street lights. Okay, the street lights that turn on in the night or it turns off in the day. That is an automatic switch. That also uses logic gate. Automatic heater that turns on when it's cold climate, the heater turns on automatically. Okay, those are examples of control systems. You control the device using a computer, automate. Okay, it's based on automatic. We are going to look at one example of the automatic system. Okay, let's go to the next one. Application of logic gate. Automatic switch for street lights. Okay, see here. Now, this diagram, you can see we have our block diagram. The first two are the sensors, input sensor. Okay, you need certain information coming in, right? So in the computer systems, they use sensors. Okay, whether they are flow of current or no flow of current. What the sensor does, what the sensor does is that they send current. Okay, the function of a sensor is to detect and then they send current, or they do not send current. And then you have the control circuit inside. So this control circuit is what I said as the brain of the computer. Okay, so this part is the brain. So the brain consists of logic gates. What is inside the logic gates is just circuits. Okay, you remember I showed you the OR gate and the AND gate, all the type of circuits, right? So they're just circuits. And then after the brain, it will give an outcome. So the computer is going to decide whether I want to do this or do that one, whether I want to switch on the street lights or I want to switch off the street lights. Okay, let's see. Now the input, how many types of input? A, B. Okay, let's say this is A, and this is B. How many types of inputs? I can go 0, 0, 0, 1, 1, 0, and then 1, 1. Okay. Now, first we are going to define. We have to define first. What does the 1 means and what does the 0 means? For the switch, okay, 1 means on. 0 is off. This is for the switch, the sensors. And then for the light sensor, you have to define what does the 1 means. 1 means in the day, there is light. Okay, there's light. 0 means in the night. Okay, there's light here and it's dark. After you define this, usually the question will give you, okay, what does it mean by 1? They will give you. If they do not give you, then you have to define it yourself. Okay, because when you put all the 1, 0, you don't know what it means. Okay, you have to first define it. Okay, so 1 is daylight, 0 is nighttime. And for the switch, 1 is on, 0 is off. So how many possible outcomes we have here? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so find out what is the outcome. So here we have a NOT gate. So NOT gate is whatever the input of B, I take the reverse, right? So if B is 0, 1, 0, 1, then NOT is 1, 0, 1, 0. And then it goes to the OR gate, 1, 0, 1, 0. A is 0, 0, 1, 1. Okay, so after the OR gate, what happened? You get the outcome. Outcome is OR gate means either one is fulfilled, right? So 1, 0, 1, 1. Okay, either one. If there's anyone has got 1, then it becomes 1. I'm going to close my camera because it's quite lagging. Okay, so the outcome is 1, 0, 1, 1. I put in the truth table. This is C and this is the X outcome. C is 1, 0, 1, 0. X is 1, 0, 1, 1. Okay, now what does it mean? You see, from the truth table, we focus on this three, this one, and this one. Okay, anything in the middle is not important. Okay, I want to know the outcome only. What does this tell you, the logic gate? You see, the first line, let's look at the first line. If switch is turned off, this is off, right? 0 is off. If switch is turned off, B is what? The light sensor. And if it's during the night, what happened to the outcome? It's a 1, meaning that the street light is switch on. Okay, automatically it will switch on. Now this one, if the switch is off and the light sensor sends light, so in the day, what happened to the switch? The street light will automatically be switched off. Okay, so next one, if the switch is on, if you manually turn on the switch, then regardless of the light sensor, now it is in the dark, right? It is sensing the no light. So this is nighttime. Regardless, you turn on the switch, this is on. Okay, you see the last line. You turn on the switch, even though it is daytime. Okay, because we don't want, if it's daytime, you turn on the switch and it does not turn on. No, we want to be able to control it manually. So whenever I turn on the switch, it must be on. The street light must on. Okay, so you can see 1, 1, when the switch is 1, it must be a 1. So on. Okay, so these are all programs. Okay, these are all programs by the logic gates based on the circuit arrangement, everything. I have created a automatic system like this. These four lines are just showing the four possible scenarios. Four possible scenarios. Okay, so it shows that this is what we want. Whenever the switch is pressed, it turns on regardless of whether it is at night or whether it is in the dark. Whether it is at night or